How's it going, everyone? This is High Yield MedCat, and today we're going to be talking about chemical kinetics, something that is rather simple but often misunderstood on the MCAT. So let's jump into our first question. We want to ask ourselves, what is the difference between thermodynamics and kinetics? Well, this diagram, the reaction coordinate diagram, can show us this difference pretty clearly. First, we see our A here. A is going to be our reactant that's going to be converted into product B. Now, in order to do that, even if it's a favorable reaction, as denoted by our negative delta G naught of our reaction, and I'll circle that here, we do need to input some energy in the form of this delta G naught double dagger. So delta G naught double dagger, and that's how we denote it, with this sort of dagger with two lines through it, is a measure of how fast the reaction goes. So that's kinetics. So that's a measure of kinetics, chemical kinetics, and that's what we'll be focused on today. Now, on the other hand, thermodynamics is a measure of how spontaneous a reaction is, and that's going to be our delta G naught of our reaction. So these are two different values, and it's important to note that these are completely independent of each other. Now, delta G naught double dagger will always be positive because we always need to put some amount of energy in to get any reaction to occur, whether that is going to be a spontaneous or non-spontaneous reaction. Whereas our delta G naught of our reaction can be positive, so if it's positive, it is a non-spontaneous. So positive equals non-spontaneous reaction. And then a negative delta G naught of a reaction is a spontaneous reaction. And to illustrate the difference between these two, I think it's useful to bring up the example of the combustion of gasoline. Obviously, it's a very spontaneous reaction, releasing a lot of energy that allows us to drive our cars over long distances. However, when you expose gasoline to air, it doesn't automatically combust. And that's because gasoline's combustion has a pretty high delta G naught double dagger. So we need some sort of energy to kickstart that reaction. And that's going to happen inside the engine of our car. Hopefully. Of course, we don't want it to happen outside of the engine of our car because then we could run into problems blowing up our car there. So hopefully that delta G naught double dagger is catalyzed, something we'll get into in a little bit, by our engine. And in our body, which is going to be relevant for the MCAT and biochemistry in particular, is that our catalysts are going to be enzymes, and enzymes are biological catalysts. And this is important to understand because enzymes only affect the delta G naught double dagger of a reaction. It has no bearing on how spontaneous a reaction is. So an enzyme will not change how much energy is released in a reaction. It will just lower this activation barrier, this delta G naught double dagger here, and allow that reaction to occur with a lower activation energy. So another term for delta G naught double dagger is activation energy. So now let's get into some of the equations that are going to be useful to memorize for the MCAT. Now, this equation is called the Arrhenius Equation, named after the scientist who discovered it. And we're measuring something in the Arrhenius Equation called the rate constant, and that is denoted by K. And K is importantly going to be in units of concentration divided by time. So most typically we see this in molarity divided by seconds. Now it's important to remember that K is an intensive property. So that means it is specific to the reaction. So the only ways that K can change is if we change some of the variables involved in this reaction. And our delta G naught double dagger is going to be our E sub A here. So this is just another way of saying delta G naught double dagger. We'll sometimes see that written as E sub A, which is shorthand for activation energy. Now, a not super important variable that we won't see very often is A, which is our frequency factor. It's basically a measure of how frequently do molecules collide in the reaction. The higher that number, the higher the rate constant. E is a constant. It is actually just Euler's number, something you probably saw in high school math. Its approximation is about 2.7 for the MCAT, although that will probably not be something you need to memorize for solving any problems. E sub A is our activation energy, something we've already been over. R is our ideal gas constant. Now that's something you definitely want to have memorized as 8.134 joules per mole times Kelvin. Now we can also see this in other equations such as Pivnert, or PV equals nRT, dealing with our ideal gas law where R is 0.0832, and this will be moles times Kelvin divided by liters times atmosphere. Now, finally, we have T, which is our temperature, notably going to be given in Kelvin. Now, just to finish up with the Arrhenius equation, this isn't something that is absolutely necessary per se to have memorized. It actually doesn't show up on that many double AAMC practice problems, but it is useful to see how manipulating the different variables will affect the rate constant of an equation. Now let's get into a formula that may actually show up a little bit more. Now this formula is kind of interesting. We have our rate, so as opposed to our rate constant. So rate is not the same thing as our rate constant. So rate does not equal rate constant. Okay. Rate constant is just accounting for the temperature, frequency factor, and the identity of the reaction. The rate itself is going to depend a little bit upon the concentrations of not only the reactants, but also the products, as we see in this equation. So I've written here that we can derive the rate from the rate of disappearance of a reactant, so how quickly a reactant is disappearing, or rate of appearance of a product. And we can do either or because when a reactant is disappearing, it will be appearing as a product. And we can see this in this equation here, where the delta just means change in a certain amount of variable. So in each numerator, we have the change in either a reactant or a product. And in the denominator, we have something called the stoichiometric coefficient. So that's how many molecules are undergoing the reaction per cycle of the reaction. And our delta T is, of course, how much time has passed given that concentration change. All right, now let's get into this practice problem here, where it says our concentration of A, or A in brackets, is disappearing at a rate of 4 molarity per second, and its stoichiometric coefficient is 2. What is the rate of the reaction? Well, the equation we're going to be using here is this one. We know that A is a reactant, and we also have all the variables we need to solve this equation. So if we plug in our values, we have negative delta A, so our delta A is going to be 4 molarity in this case, and this is also going to be negative because A is disappearing as a reactant. So a negative times a negative will yield us a positive. A, our stoichiometric coefficient, is 2, and then our delta T is just 1 second. So we have that 4 molarity per 1 second. Now if we take a negative of a negative, that will give us positive 4, and positive 4 divided by 2 will give us 2. So our rate is 2 molarity per second. So that is the total rate of our equation, even though the concentration of one individual reactant, A, is disappearing at a rate of 4 molarity per second. The reason the rate is different is that the stoichiometric coefficient is 2. So even though A is disappearing at a rate twice that, the reason for that is that 2 molecules of A participate in the reaction per cycle of the reaction. Now let's get into what is definitely the most high yield topic in this section, is rate law. Now I've written out a few notes here, In rate law, we're going to be interested in how the rate constant and the concentrations of notably our reactants, and not our products, are going to yield us our total rate. So remember, K depends on our intensive properties of the reaction and the temperature. So that's going to be the Arrhenius equation that we were looking at. And now we're also taking into account what we looked at in the previous slide, the concentration of our reactants, specifically general reactants A and B. Now something that is super high yield and something that MCAT test writers will try to trick you about is that our exponents for our rate law, x and y, are completely independent of our stoichiometric coefficients. So those are going to be little a and little b. They are not the same thing. They are totally independent, and if they are the same, that's just happens by chance. That is a coincidence. So it has nothing to do with the stoichiometric coefficients themselves. Now we can label reactions in different ways depending on the sum of x and y, and perhaps even z if it depends on a third reactant. And we can label them based on these things called order. So a first order reaction has the sum of the exponents in the rate law add up to 1. Second order has them add up to 2, and third order has them add up to 3. Now we could go 4th, 5th, 6th, and 7th, but those get increasingly more rare. So mostly on MCAT you're going to be dealing with first, second, and third. We also have 0th order reactions. And that's going to be where the rate law is entirely dependent on our variable k and nothing else. So let's take a look at this brief practice problem that says, what order is the following SN1 reaction? So harkening back a little bit to our organic chemistry concepts. So the rate law is written as K times the concentration of A. Now to determine what order the reaction is, we need to sum the exponents. And we only have one exponent, and it's 1. So this reaction is a first order reaction. And the reason for that is that in any SN1 reaction, our transition state is going to be created by the formation of a carbocation. So let's say we have this molecule here, and our rate limiting step is going to be this water coming off the molecule and this carbocation forming. And then our nucleophile is going to come in. But that's actually a faster step than this first step, which is slower. So the formation of the carbocation is our slow rate limiting step, which is going to determine the order of the reaction. So actually, the A here is going to be the concentration of this reactant with the alcohol group. That is going to be our A in this SN1 reaction. Now another thing we could think about with this problem is what the units of K have to be in an SN1 reaction. Now K necessarily has to be 1 divided by seconds because eventually rate has to be in molarity per second. And if A has an exponent of 1, it will have the units of just molarity. So if we multiply that by 1 divided by second, we get molarity times second. So to go over that, we have K equals 1 over second times molarity will give us our correct units, which is molarity over a second. Now finally, let's finish up with this double AAMC or double AAMC-like practice problem that I've written here. So this is very similar to something you might see either in a freestanding question, or if this table were part of a passage-based problem. And this is going to be very physiologically relevant because this is something you may have seen in AP Bio or Intro Bio, the electron transport chain, notably where our O2 is our final electron acceptor. If that looks totally foreign to you, you may want to go back and study a little bit on the electron transport chain, which is going to occur, of course, in the inner membrane of the mitochondrion of our cell. Now, we have our practice problem here. So I'll give you a little bit of time to read it and then think about how maybe you want to go through the problem and see if you can come up with an answer on your own before we get into how we solve this problem. All right, so hopefully you've taken a little bit of time to read this question on your own. Now let's get into how we actually solve these types of problems. This table above is showing 3 trials that are helping us determine our rate law of the reaction. And we have 4 potential rate laws in our answers that we're going to choose from. Now each trial you can think of as being paired with a different trial, where one is our quote-unquote control and the other is our experimental. So let's take a look at trial 1 and 2 together first. We see that in trial 1, we have 3 molarity and 3 molarity for both the concentration of O2 and H+. And this yields a rate, which is our dependent variable in the rate equation, of 5. So the way we could write this out is 5 molarity per second is equivalent to K times 3 to some exponent times 3 to some exponent. And the exponents x and y, of course, are what we're looking for. Now, we notice that in trial 2, the concentration of H plus has remained the same, but we've multiplied by 2, 3 to get 6. So we have 2 times the amount of O2. And we'll notice that our rate, similarly, has increased by 2. Now, this should make sense if our exponent x is 1. So if we have 10.0 molarity over second times k times 6, and then x, and then 3y, the only way this will necessarily be true is if x is equivalent to 1. If x was equivalent to 0, the rate wouldn't change, and if x was equivalent to 2, the rate would actually quadruple, because 2 squared is 4. So that would quadruple our rate. So we found x. So x has to be equivalent to 1, which means our exponent for O2 has to be 1 in our rate law. So we can eliminate answers B and D because they both have x equals 2 for our rate law. Now for a second half of our problem, we can take a look at a different pair of trials. Let's take a look at 2 and 3. Now in 2, which we've already examined, we have 6, 3, and 10, whereas in 3 we have 6, 9, and 90, where this time we've changed our H plus concentration and kept our O2 concentration the same. Now this time, instead of doubling the concentration, we have tripled the concentration of H plus. However, that has multiplied our rate by 9. So this is going to be a little different. So let's take a look at this equation. So our rate is 90 molarity per second is equivalent to our K times our 6 to the X, which we know is 1, and then times 9 to the some exponent Y. We don't know which one that is yet. However, it stands to reason that if we have tripled our concentration of H plus and then multiplied by 9 our rate, that our Y has to be 2, because 3 squared is equivalent to 9. So if we multiply this by 3 in here, and then we square it, we multiply our rate by 9. And that's how we get from 10 to 9, even though we've only tripled that concentration of H plus. If our exponent was 1 instead of 2, we would have 30 molarity over second be our rate. And if it was 0, we would get the same rate. We would get 10 molarity over second. So we know x equals 1, y equals 2, which is consistent with answer C here. Now this is going to be a very paradigmatic or very representative problem of what you might see on the MCAT. That's it for High Yield MCAT. Feel free to like, subscribe, and leave a comment letting me know what topic you would like to see next. Also feel free to check out my free amino acid playlist that can be found in the link below.